All right, guys, today we are talking about derivatives. And hopefully we don't get interrupted too much by the intercom here, but they might beep in every once in a while. The derivative is one of our first big topics here in, it's really a giant topic in calculus, but a derivative is really helping us find the slope. Okay, so when we're looking for derivatives, what we're dealing with is slope. But what the derivative is actually doing is it's not just helping us find a slope. When we're finding a derivative, what that is doing, it is helping us derive a formula for the slope, not just at a single point. It's us deriving a formula for the slope at any point on the function, which is really powerful because it helps us find that rate of change at any point, not just a specific point. So earlier in the class, we were looking at the slope of our secant line, and we were using that to help us find the slope at a specific point. Okay, so we were finding the slope at a specific point. Now what we want to do is we want to take that same formula, and we saw this one earlier, and we want to use that to help us derive another formula. We want to use this formula to find another equation. So as my limit of h goes to 0 of this formula that we've seen already, remember on the bottom, this was how much our x was changing as we got closer to 0. And this was how much my y is changing on the top. We're going to use that formula to help us find another equation. All right, so this is the one that we're really going to focus on today. It's going to kind of be our bread and butter. Another way that you might see that is my limit as x goes to 0. And remember, this delta y over delta x means as my y changes over my change in x. So this is just the same formula, but this time instead of using h, they're using delta x. And we're really not that interested in, I want you to recognize this formula, but we're going to focus on the one with the h. It's just a little bit easier as we're doing these problems rather than dealing with delta x if we're just dealing with h. But it's the same formula, just written in a different way. All right. So this bottom one we'll come back to in a little bit, but let's just look at an example. We're going to find the slope of the graph at point -1,3 of this equation. Now, if you look at this equation, a lot of you can already tell me what the slope is because it's in point slope. It's the point slope formula, but we're going to use this easy example to show you how this formula works. And then we'll get on to a little bit more complicated formulas. So basically what we're doing is we're taking this, and I'm going to write it down here so we can use it. We're taking this f of x plus h minus f of x over h. And we've got the limit as h goes to 0. So I'm going to use this limit, and I'm going to apply it to my function right here. So the first thing that I always do, my limit as h goes to 0. Anytime I'm doing this, the first thing that I always do is write my bracket, and then I'm going to do minus my parenthesis, and I'm going to put that over h. So I usually write that first, and then I'm just going to fill in the pieces. So my minus f of x, that's just minusing my f of x or minusing my function. So I can just write my function right in the parentheses. Now my bracket, instead of f of x, I have f of x plus h. So anywhere that I see an x, I need to change that to an x plus h. So in my bracket, I'm going to put -2, but instead of x, I'm going to put x plus h, and then I have a plus 1. So inside the bracket, I rewrite my function. I just replace my x's with x plus h, and then I have h on the bottom. So now we're just going to start simplifying. The limit is still here, but we're going to focus on simplifying our equation here. So my limit as h goes to 0, I'm going to go ahead and distribute the -2. So that becomes negative 2x minus 2h plus 1. And then I'm also going to distribute this negative. So that becomes a plus 2x, and a negative times a 1 is a minus 1. Now, if you do this correctly, everything inside this parenthesis should end up canceling, because my positive 2x and my negative 2x cancel. And my negative 1 cancels with this positive 1. So my limit as h approaches 0, everything is canceled on top. I've got negative 2h on top. Not everything is canceled, but everything from my parentheses canceled. And then I have h on the bottom. And now I can cancel my h's. So my limit as h goes to 0 of negative 2. I don't have any h's to plug in my 0. So my limit as h goes to 0 of negative 2 is just negative 2. So my slope is negative 2, which we already knew. Again, this is a line. So finding the slope of a line is really easy because it doesn't change. My line always stays the same. So my slope is negative 2 all the time. Now, when I'm not dealing with a line, instead of a simple answer like negative 2, I'm going to actually end up with a formula. It's a little bit more because my slope changes at each point. So for example, we're going to use that same formula, but we're going to apply it to, we're looking for the slopes of the tangent lines at these two different points. So f of x equals x squared minus 1. So again, I'm going to take the limit as h goes to 0, and I'm going to draw my brackets minus my parentheses all over h. Now, inside my parentheses, I just plug in my f of x, x squared minus 1. Inside my brackets, I'm going to use the same equation, but this time instead of x, I have to use x plus h. So it's x plus h squared minus 1. And then we're going to start simplifying. So I'm not going to forget about my limit, but I am going to focus on this part for now. So inside my bracket, x plus h squared, you can go ahead and FOIL that out if you need to. But that becomes x squared plus 2xh plus h squared. And then I still have a minus 1. And then minus x squared when I distribute the negative, and that's going to become a plus 1. And that's all over h. So we've got x squared plus 2xh plus h squared minus 1. I don't need those brackets anymore. Minus x squared plus 1. I probably could have left them out in the last step. But remember, if I did this correctly, everything that came from the parentheses, this negative x squared should cancel out. This plus 1 should cancel out. So I know that I did it right, or at least it looks like I did it right. So I'm left with my limit, let's not forget that that's there, of 2xh plus h squared all over h. Now I can go ahead and cancel out an h because I got an h on the bottom and an h in everything on top. So those are going to cancel, and I'm going to be left with the limit as h goes to 0 of 2x plus h. And I think that's as much as I'm going to be able to simplify it. But notice this time, I'm not just left with a number. I still have an h and an x in here. I actually have an equation. So as h goes to 0, as h becomes 0, my limit as h becomes 0, that becomes 0, and I'm just left with 2x. So my limit becomes 2x. It becomes an equation. And that equation is our derivative. That equation that we found when h goes to 0, that equation becomes our derivative, which a lot of times we call f prime x. So that is my formula to find the derivative, or to find the slope, excuse me. That's my formula to find the slope at any point. All I have to do is plug an x value into 2x, and it tells me what my slope is. So let's go ahead and do that. Let's plug in our 2 points. So if my f prime of x is equal to 2x, let's plug in 1. So when x is equal 1, then my slope is going to equal 2. So my f prime of 1 equals 2. My f prime of negative 2, when I plug in a negative 2, that equals 2 times negative 2, which equals negative 4. So my slope at negative 2 is equal to negative 4. So this is a really powerful thing that we can do, because we can take any equation, any function out there, and if it has limits, if it has a limit, then we can find the derivative so that we can find the slope at any point on that graph, on that function. Okay. All right, so a couple of formulas, a couple of notations that you need to be aware of. So we just found that this f prime of x represents the derivative. That tells us that we're finding the derivative. So the derivative is equal to our limit as our change in x goes to 0 of our slope secant formula. So again, this is just like if this was h and this was h and this was h. In fact, I like it with h a lot better, but I want you to see it both ways. So I wrote it for you down here with the h. My dy dx is equal to my limit as my change in x goes to 0 of our change in y over change in x. So this is just another, these two are the same, mean the same thing. It's just another way of writing it. So as our x goes to 0, as our change in x goes to 0, why are we looking at change of x? This shouldn't be an h. This should be a change in x again. Sorry. Like I said, I like to use h, so I'm in the habit of plugging h in there. But it's just showing you that it's the same thing, that it's the same formula. So you're going to see a lot of different notations for, and again, don't worry about this stuff too much. What we're focusing on is that formula right there. Oh, well, we better include the limit. We're focusing on that formula right there. But there's a lot of different notations for that formula. If you see f prime of x, it wants you to find the derivative. If you see dy over dx, it wants you to find the derivative. If you see y prime, it wants you to find the derivative. D dx of f of x wants you to find the derivative. Okay? If you see d sub 2 of y, it wants you to find the derivative. Now, this one is really rare. We don't see that one very often. You are going to see f prime of x a lot. You are going to see dy dx a lot. Y prime, these two are going to come up a little bit as well. But these two on the left, those are the ones that you are going to see the most this year. But be familiar with them all. They all mean the same thing. And that just is, use that limit formula as h goes to 0 of f of x plus h minus f of x over h. All of these mean find that limit to find the derivative, okay? So let's do some more examples. Well, before we do, and we should have checked this before, but we found the derivative of x squared minus 1. We think that our slopes down here were, we thought that our slope was 1 and our slope was negative 4. We can actually double check that. If I go to y equals and I plug in x squared minus 1, and I go to the graph, that is a terrible window. Let's do our standard window. Nope, zoom, standard. There we go. So here's my x squared minus 1 function. I want to know was I correct? Were the tangent line slopes, did I find the derivative correctly? So the way that I can check that is let's just draw the tangent lines and see what the slope is. So remember, to draw the tangent line, I do second draw, and I want to draw a tangent line 5. And my first tangent line I want to be at x is equal to 1. So when x is equal to 1, there's my tangent line, and it gives me the formula. The formula is 2x plus negative 2. And if I factor out that 2, oh, sorry, that was my slope. My slope was 2. I was reading f of 1. So my slope at 1 is 2. So we did that one correctly. Now let's look for the slope when x is equal to negative 2. So if I do the same thing, second draw a tangent line, but this time I want to draw it at negative 2. So there's my tangent line, and it's going to give me my formula down here. Y equals negative 4x plus a negative 5, which is exactly what I wanted. My slope is negative 4. So we can check if our tangent slopes are correct. We don't always have the calculator though, so don't rely on it too much, but just know that that's something that you can do. All right, so let's find the derivative of f of x when it equals x cubed minus 2x. So I am looking for f prime of x. So we're looking for the derivative of this function. So my limit as h goes to 0, I'm always going to start the same way, is a bracket minus a parenthesis divided by h. All right, sorry about that interruption. So I always start with this outline. And remember, in the parenthesis, I plug in x cubed minus 2x. And in the bracket, instead of x, I need to put my x plus h. So this becomes x plus h cubed minus 2 multiplied by x plus h. Everywhere there is an x, I need to put an x plus h. So as you're looking at this, you can see there's a lot of places to make mistakes. Hopefully we don't make any today in the video. But as you're doing these, if you're going too fast, sometimes you can make mistakes. So we're going to be trying to be a little bit careful as we work through. I mean, none of this part is calculus. Now we're just dealing with algebra. So I've got x plus h cubed. So the first thing I need to do is expand that out. So x plus h cubed means x plus h multiplied by x plus h multiplied by x plus h. So you can do that a couple of different ways. You can FOIL the first two and then multiply everything by x and multiply everything by h. You can multiply them one at a time, or if you remember Pascal's triangle, it looks something like this. We have a 1 on top, and then a 1 and a 1, and then a 1, 2, 1, and then a 1, 3, 3, 1, and it keeps going 1, 4, 6, 4, 1. And if you remember, we can apply this to something risen to a power. So if we have a power of 0, we use the first row. If we have a power of 1, we use the second row. If we have a power of 2, we use the third row. But we have a power of 3. So we are interested in the 1, 3, 3, 1. And the way that we apply that is when we have x plus h cubed. The first thing that I get is one of my x's. I get 1x, and that's raised to the third power. That's where the 1 comes from. Then I have a 3, but this time I have x's and h's. And what I do is I lower my x exponent by 1, and I add an h. Then I have another 3, and I lower my x exponent again to just x, but I raise my h exponent to 2. And then I have a 1, And this time I lower my x exponent again, so the x's go away, and I raise my h to the third power. So you can FOIL it and multiply it, or if you can remember Pascal's triangle, you can use that method. So this piece right here becomes, and I'm going to give myself a little bit more room here. That x plus h, I'm going to leave my brackets for now, becomes x cubed plus 3x squared h plus 3xh squared plus h cubed. But I'm not done because I have this -2 that I need to distribute as well inside my bracket. So I get -2x minus 2h, and I still have this stuff on the outside. Well, that's everything inside the bracket. But now I have this negative that needs to be distributed. So negative x cubed plus 2x's. And all of that is over a simple h. So let's see what we can do to simplify things here a little bit. I can get rid of the brackets. So I've got x cubed plus 3x squared h plus 3xh squared plus h cubed minus 2x minus 2h minus x cubed plus 2x. And all of that's going to be over h. So my x cubed cancels with my negative x cubed, and my 2x cancels with my negative 2x. So I'm left with 3x squared h plus 3xh squared plus h cubed minus 2h, all over h. So from here, everything has an h in it, so let's go ahead and cancel out the h. Let's get rid of this h, and this h is going to go, instead of h squared, that's going to just become h. This h is going to cancel. We better write this out. We're starting to get lots of canceling. So we're left with 3x squared. This h cancels. We have plus 3x. Instead of h squared, we canceled one of those h's. Plus h cubed. Now we have h squared. And then we have minus 2h. And don't forget that we still have a limit as h goes to 0. So the limit as h goes to 0 of this new yucky equation. Well, as h goes to 0, 3x squared doesn't change. But as h goes to 0, 3x times h, when h hits 0, that becomes 0. And h squared, when it becomes 0, becomes 0. And minus 2h becomes 0. Oh, I shouldn't have an h there. I'm looking at that thinking something's wrong. See what happens? We all make mistakes. That h right here canceled out, and I was supposed to just write minus 2. So this minus 2 doesn't cancel either. There's no h with it. So I've got 3x squared minus 2. So my limit as h goes to 0 of all of this, my limit becomes 3x squared minus 2. And that becomes my f prime of x. That's my derivative. I can plug in any x value and find out what my slope is going to be. And I think it gave me, did it give us a specific value? It didn't give us a specific value. It just wanted us to find the equation. So f prime of x is 3x squared minus 2. Okay? So be careful with your algebra. It's easy to make those mistakes. It's easy to forget to cancel something out, especially when you're working quickly. So let's do a couple more. I think kind of the best way to do these is just to keep doing them and seeing them. So we're going to work through a couple of more. We're not going to worry about this one today, at least not on the video. But it wants us to find the derivative, and then it wants us to plug it in, plug in x's and see what the slope is. So I'm looking for the derivative of f of x. So I'm looking for my f prime of x of this function. So we're going to take the limit as h goes to 0 of, here's my bracket, minus my parenthesis all over h. So in the parenthesis, I just put my function. But in my bracket, instead of the root of x, I have to put the root of x plus h. And that's going to go on top. So we have kind of a mess. We've got a bracket with a root under it, and we have another root. And I want to simplify things. And one of the things that I always think about when I see roots, one of the first things I want to consider is a conjugate. So on top, I've got root of x plus h minus root of x. I'm going to multiply by the conjugate to see if that simplifies a little bit. So I'm going to multiply by the root of x plus h minus, or not minus, plus the root of x. I'm already minusing root x. Now I want to plus root x. And if I do that on the top, on the bottom, I have to multiply by x, root of x plus h plus root of x. So let's see what happens. On the top, a couple of ways we can do this. We're foiling. Remember, some stuff is going to cancel out. But to show you that one more time, let's just go ahead and use our table here. I've got the root of x plus h and negative root of x. And then here I've got the root of x plus h and a positive root x. So when I multiply these two together, I'm left with x plus h. Root of x plus h times a negative root x is negative root x times root x plus h. That's ugly. But root of x times root of x plus h is positive root x times positive root x plus h. And remember, those cancel. So even though they're really ugly, they're going to cancel out anyway. And then root x times negative root x is what? Negative x. So all of this on the top just becomes my limit as h goes to 0. My top becomes x plus h minus x. And I still have the bottom that I need to distribute. So I've got h multiplied by the root of x plus h plus root x. And I'm not going to actually multiply that. I'm not going to factor or distribute that x through, because before I do that on the bottom, and you should always, before you distribute on the bottom, these x's are going to cancel, which means I have h on top, and on the bottom I have h root of x plus h plus root x. And the nice thing here is my h's cancel, the top and the bottom. So I'm left with 1 on top, and I've got what on the bottom? Root of x plus h plus the root of x. Now remember, I'm still taking my limit as h goes to 0. Looking at this, I don't think I can do much more with that. So let's see what happens when h becomes 0. I still have 1 on top. The bottom becomes root x because h becomes 0, plus another root x, which just becomes 1 over 2 root x. That becomes my derivative. That's my f prime of x. My h's are gone. They all turned into 0. And I'm left with 1 over 2 root x. Okay. Now to evaluate this function at those points, the slope of the function, I've got to plug in these x values. Now, when I plug in -2, so if I take the f prime of -2, so just meaning I'm going to plug in -2, I get 1 over 2 root -2. Root -2, I can't take the root of a negative number. That's an imaginary number. So this one, I'm not allowed to do that. So this one does not exist. Well, it's undefined. That's a better word to use. There is no slope at that point. Okay. F of 0, 1 over 2 root 0. Well, the root of 0 is 0. times 2 is 0. So this becomes 1 over 0, which is also undefined. So at those 2 points, the slope is undefined. Probably because there's going to be holes at that point, right? Now, f of 2 equals 1 over 2 root 2. Now not f of 2. These are f primes. F prime of 2. When I plug 2 into the derivative function, f prime of 2 is equal to 1 over 2 root 2. Now, back in Math 2 and Math 3, we would make you rationalize the denominator. We would make you multiply to get rid of that root 2 on the bottom. Not in calculus. Remember, calculus, even on that AP test, they don't care if you simplify beyond that point. So your answer for that one, f prime of 2, can go ahead and be 1 over 2 root 2. That's an acceptable answer in AP calculus, okay? So we were able to find the slope, not at every point, but we were able to find the slope at f prime of 2, okay? So a couple of things to keep in mind. Functions for which the derivative exists at all points are called differentiable functions, okay? Some graphs that have things like sharp turns, or like the absolute value graph, has it has a point, it has a sharp turn. We call that a cusp. If it has a vertical tangent, or if it's not continuous. For example, the square root function. This is not continuous because as I come to the left, I have to stop at 0. It doesn't keep going. So functions like this, sometimes you can find a derivative, but that doesn't mean it's differentiable everywhere. So like this example that we just did, we found a derivative, we were able to do that, but we weren't able to find a slope everywhere. The slope didn't always exist. So it's not differentiable at every value because of that square root. That made it so we're not going to be able to differentiate everywhere. Okay. So a quick example, and then we'll let you get onto some practice. Okay. So what this is saying is f of c equals the limit as x approaches c of f of x minus f of c over x minus c. So what this is saying is at this point, it's differentiable if and only if the limit exists on the left, a limit exists on the right, and those limits are equal. Or in other words, if this is continuous at that point, okay? So what it's saying is f is differentiable at this point if f is continuous at that point. Or in other words, if there's a hole in the graph, if I have a quadratic function, but I have a hole, there is no slope at this point. If it's not continuous at that point, we can't find a slope because there's no slope to find. There's a hole in the graph. If I have a sharp turn, I can't find the slope at that point because it's a sharp turn. Okay, even though it's continuous, I can't find a slope there. Okay, so watch for that. For example, find the derivative at x equals 3 of this function. Well, if I graph that function, this is just the absolute value function, but it's not just the absolute value of x, it's the absolute value of x minus 3. So I'm actually shifting to the right 3. So when x is equal to 3, I've got a point right here, which means it is not differentiable. Okay? We can't find a derivative at that point. Even though it's continuous, we can't find a derivative. So that's where you need to be careful. If a function is differentiable, then it's continuous. Okay? This function was continuous, but it's not differentiable at every point. because at this point, even though it's continuous, it's not differentiable. So this is applied. If it is differentiable, we know that it's continuous. But if it's continuous, that doesn't mean that it's differentiable.